day, grade 11 chemistry students. Today, what we're learning about is something called limiting reactant stoichiometry. Okay, our learning goals, again, basically deals with two things, something called percentage yield and limiting reactants, and that's what I just talked about. And both of these involve stoichiometry. So we are going to start off with a balanced chemical equation, and then I'm going to show you how you determine it's a limiting reactant type question, and then how to solve the problem. So here we go. So we're going to start by defining limiting reagent or reactant stoichiometry. And we want to discuss something here first, stoichiometric amounts. So they represent the amounts that are in the exact ratio of the balanced chemical equation. So for example, if the coefficients are 1 to 2 to 3, then the amounts that we have in that, specifically with the reactants, will be in 1 to 2 to 3 as well. Now, reactants are completely used up when the reactants are in perfect stoichiometric amounts. What happens is when they are not in perfect stoichiometric amounts, some reactant is left over and one is used up. So in everyday practice, when we're actually doing a lab, reactants are not always they're not in stoichiometric amounts. One is always in excess of the other. So let's quickly just talk about an example to help you understand what limiting reactants is. So this weekend for Easter, my grandmother made a salad, and what it took was 1 head of lettuce, 2 cucumbers, plus 5 radishes, and that makes a nice, wonderful grandma salad right there. So the question is, it's like a balanced chemical equation where the ratio is 1 to 2 to 5 to 1. Now, something important before we start the analogy is that if you don't have exact amounts, you can't make a partial salad. I know that you can in reality, but with molecules and compounds in chemistry, you can't make a partial salad. So if we don't have 5 radishes, if we only have 4 radishes left, even though we have 2 cucumbers and 1 lettuce, we can't make a full salad for this analogy to work. So here's a question before we begin. How many salads can be made from the following amounts of ingredients? We have 2 heads of lettuce, 16 radish, and 5 cucumbers. So let's go back to our example and look at this. So our amounts are 2, 5, and 16, and the question is how many salads can be made? When we know the ratio is 1 to 2 to 5, which equals 1 salad. So let's start off by getting all our ingredients and just showing you what they look like. Okay, so here I have all my ingredients. 2 lettuce heads, 5 cucumbers, and 16 radish. Now, what's the maximum amount of salads I can make using this recipe? Remember, we can't have partial salads because grandma is very fussy. She wants the complete recipe, so you can't have partial salads. Now let's take a look at how many salads we can make with this many radishes. Well, if we have 16 radishes, the ratio is 5 to 1 between the radish to the salads. So if I have 16, that means I can use 15 of them. And 15 divided by 3 means I can make 3 salads. Okay, so that means I have 3 salads and I have 1 leftover radish right here. Okay, so that's kind of a problem, but I just have to leave that alone. Next, what we have is we have cucumbers. If we look at this, 2 cucumbers means 1 salad's a 2 to 1 ratio here. And we have 5 salads, so that means I can use 4 of them. Okay. And I can make 2 salads because it's a 2 to 1 ratio, but I'll have 1 cucumber left over. Okay, well, that's fine. And then finally, we have 2 heads of lettuce, and the total amount of salads that I can make is 2. Okay, so you see this? Because 2 to 1 ratio is the ratio between, oh, sorry, I apologize. It's a 1 to 1 ratio. So if I have 2 heads of lettuce, I'm going to make 2 salads. Now, why do we care? What does this have to do with chemistry? Well, the reason is this here is what we call my limiting reactant. And the reason is, actually, both of these are, because we can make only 2 salads based on these ingredients, whereas here, we can make 3. Now that means because I can make 3, I can't really make 3 salads because I only have enough to make 2 salads based on my other ingredients. And if I make 2 salads, what will happen is I'm going to use, 2 heads of lettuce. I'm going to use 4 cucumbers. And if we take a look at this, I'm going to use 10 radishes. And I'm actually going to have left over 6 of these guys. This is what's going to be left over. So we call these two would be my limiting reactant, and this one here is going to be my excess reactant. In other words, I have way too much radishes, Oma. Sorry. So you don't know what an Oma. Oma is my grandma. So grandma has too much radish. She has one too many cucumbers, and her limiting reactants are really her lettuce here. Okay. So we can write this down. The limiting reagent or reactant is the reactant that runs out completely and determines the amount of products produced. The excess reagent is the reactant that's left over after the reaction is complete. We can't make any more product, and we have some stuff left over, just like our radish. So let's actually go ahead and do this as a practical example. It says solid lithium nitride reacts with water to form ammonia gas and aqueous lithium hydroxide. Now it says if 4.87 grams of lithium nitride reacts with 5.8 grams of water, how much ammonia gas is formed? Now, first of all, let's take a look at what information we have. We have 5.8 grams of water, and we have 4.87 grams of lithium nitride. It's asking us to find out how much ammonia is going to be produced. So I have check mark these two values. I want to find this mass amount. Now, it doesn't say how much, so I guess, but I'm actually looking for mass here. So how much mass of ammonia will be produced? This is limiting reagent, guys, because it gives you 2 reactants masses. This is stoichiometry because it gives you information on some chemicals and asks for information on other chemicals. So therefore, it's stoichiometry. So we're going to set it up exactly the same as we did in our previous stoichiometry questions, where we have to balance a chemical equation. Okay, so I balance a chemical equation, and we have a 1 to 3 to 1 to 3 ratio after you write this chemical down, all these chemicals down. Then we're going to write down our values that we have. Values that we have are 4.87 grams of lithium nitride, 5.80 grams of water, and we want to find the mass of ammonia that's produced. Now we recognize this is a limiting reagent because we have 2 reactants. We want to find a different chemical based on our information here, and that's ammonia, and so therefore it's stoichiometry as well. The steps that I'm going to take today, and there's several different ways you can do limiting reaction stoichiometry, but remember, I'm going to find out how many moles of ammonia I produce from both this compound here and this compound here. So I'm going to hop to NH3. The one that produces the least amount is the correct answer, okay? So let me show you what I mean. So again, we are going to convert to moles because that's how we can use these ratios to do something that I like to call the molar hop. So I'm going to convert to moles of lithium nitride. I'm going to find out how many moles of water I have. Once I do that, I'm going to hop from here to here using the ratios 1 to 1 because it's a 1 to 1 ratio. I'm going to hop from here to here, which is a 3 to 1 ratio. And the one that produces the least amount is the limiting reactant, and that's going to be our correct answer. So let's do that now. So we are going to find the moles of lithium nitride first. We are then going to molar hop or use stoichiometry 1 to 1 ratio to NH3. The one that produces less will be our correct answer. We start by knowing that moles is equal to mass divided by molar mass. So I'm going to have to find my molar mass of lithium nitride, which is 3 lithiums and 1 nitrogen or nitride. So I found the molar mass is 34.83 grams per mole. That's based on 3 lithiums and 1 nitrogen. We're going to plug that in there. We're also going to plug in my mass, which is 4.87 grams. And to include my units, I'm going to find the amount of moles. I like to show my division by multiplying by 1 mole over the molar mass. It is the same thing, but look, your grams cancels out. Oh, sorry, and you get 0.14 moles of lithium nitride. Recall, what kind of moles do you have? Well, I have lithium nitride. Now what we're going to do is we're going to hop from our lithium nitride to our ammonia using the 1 to 1 ratio. So now I'm going to set up the molar hop. which I'll set up right up here so you can take a look at it underneath our equation. Okay, so now we're going to perform our molar hop, and what we do is we write down the type of moles we have, 0.140 moles of lithium nitride, and we're going to write our units. So our type of moles goes up there. We write our type of moles that we want to get rid of, which is obviously going to be the same. We write the type of moles that we're hopping to. So I'm hopping to NH3, so I write that on the top. Now we have to put some units in here that make sense. Well, it says it's a 1-to-1 ratio. So for every 1 NH3, I put that with NH3, I actually react 1 Li3N. So if we write that out, that means that our mole value is not going to change, but our units are going to change. Now this makes sense because for every 1 mole of this, I make 1 mole of this. So if I have 0.140 moles here, I will end up with 0.140 moles over here underneath NH3. Let's make sure. So we're going to get another value for moles, but recall that the one that makes the least amount of moles is going to be the correct answer. Okay, so we're going to do the same thing for H2O that we just did for lithium nitride. We found out how many moles of NH3 we should produce from lithium nitride, but now we're going to check the same thing with water, okay? So again, we know moles equals mass divided by molar mass. You should know that a molar mass of water is 18.02 grams per mole. So therefore, we can just fill in our numbers. I have my sample value, I have 5.8 grams, and each mole weighs 18 grams per mole. So again, I like showing this step like this, 5.8 grams divided by the molar mass, and we get an answer. So when we divide that, we get 0.322 moles, okay? So we have 0.322 moles here. What we're going to do next is we're going to molar hop to the amount of ammonia. Remember, it's a 3-to-1 ratio, so I should be dividing by 3 as I go across. Let's do the molar hop to check. I'm going to write that right up here. Write down the type of moles you have. So we wrote down 0.322 moles of water. We want to cancel out H2O. We want to go to ammonia, so we write that on top, NH3. The ratio between those is 3-to-1. So in our calculator, we're just going to multiply by the top number, divide by the bottom number, and we get this answer. So we have 0.107 moles of NH3 according to our water. Now our water units canceled out. We got NH3. There we go. So this is our answer right here. Now remember, we did 2 steps. We had one from lithium nitride where we produced 0.140 moles of ammonia. And our other step, convert to moles, do the molar hop, we had 0.107 moles. So we have 2 answers. Well, which one is correct? Do we produce 0.107 moles or do we produce 0.140 moles? Well, the answer is that we produce 0.107 moles. This is impossible. We cannot produce this much. This tells us that water is my limiting reagent because it produced less product. As well, then that means the opposite one has to be in excess. We have too much of it. I obviously can't produce 0.140 moles. I can only produce the least amount, so 0.107 moles is the correct answer. Now, we didn't quite complete our question because we wanted to find the mass. So our last step is just like normal stoichiometry. We are going to find the molar mass of ammonia, which in the interest of time here is going to be 17.04 grams per mole. We are going to produce 0.107 moles because that's the less of the 2, and we're going to just find our mass. I'll show you that last step below right now. So my mass is equal to my moles times my molar mass, so it's 0.107 moles multiplied by my molar mass, which is 17.04 grams per mole, which is over 1 mole. Moles will cancel out, and we get a final answer of 1.83 grams. So if you add these 2 reactants together, what you will end up getting, if you add these 2 masses together, you will get 1.83 grams of product. Just to go over what we did again, because this can be a little bit confusing. So we had 2 masses, so therefore we knew one was going to run out first. To determine which one was going to run out first, we determined which one made less product. That means we had to convert both the moles, do the molar hop to the same product. The one that produced less was the limiting reagent. In this case, it was water, produced less, and then we hop from that moles that we produced to the lesser of the moles and to the product in terms of mass, multiplying by the molar mass, and that's the answer. Now, one more thing. We call this our theoretical yield. It's theoretical because that's the mass that's based on my reactants. So that mass was calculated from my reactants. Now, if we actually did this experiment, we probably wouldn't get that yield. We'd get close if we did it well. If we did the experiment poorly, we would get nothing like it. So the experimental yield is what we get from the experiment. The theoretical yield is what we get from the actual reaction. You say the theoretical yield is the theoretical mass of product calculated from the limiting reactant. The experimental yield is the amount of product actually produced in an experiment. If experimental yield and theoretical yield are very close, if they're the same number, then you have 100% yield. That means you got what you should have. The way we calculate percentage yield is by taking the experimental and dividing it by the theoretical yield and multiplying it by 100%. So, for example, if I was supposed to produce 50 grams according to stoichiometry, that's what I theoretically calculated, but I only produced 25 grams of product, 25 divided by 50 times 100 is 50%. That means I didn't do the experiment very well. So percentage yield is a way for chemists to tell if you did an experiment correctly. To help you understand, we're going to take a look at our theoretical yield from our previous question, 1.83 grams of ammonia. Well, imagine that in the experiment that I did exactly like this with the exact same reactants and amounts, but I actually did it, and I only produced 1.50 grams. That's my experimental yield. Let me show you how I would calculate my percent yield. So recall, I said in the experiment we actually made 1.5 grams of ammonia, but when we calculated that experiment, we said from our calculations 1.83 grams. Now, how do we find the percentage yield? Basically, you're just going to plug in 1.5 grams right into the experimental yield part here, and 1.83, put it in here, divide them, multiply it by 100, and you get a percentage. 82%. So this tells me that the experiment went okay. A really good percentage yield, normally, depending on the lab, of course, would be around 90%. So this is an okay experimental yield. We're going to actually do this in class where we calculate the theoretical yield using stoichiometry, specific limiting reagent stoichiometry, and then calculate the percentage yield after we've done the experiment. So that's it for today's lesson. Hope you enjoyed your night, and we'll see you soon.